Hello everyone. In today's video, I'm sharing with you how to use prime factorization to solve questions involving perfect squares and square roots. First and foremost, let me go through what are perfect squares and what are square roots. Now, perfect square is similar to the idea of area of a square. Okay, so let me write down for you. So it's really similar to area of a square. So for example, if I have a square of side 2 cm, so the area will be 2 times 2, that gives me a 4. So 4 is a perfect square. So if I have a square of side 10, then the area will be 100. So it means that 100 is my perfect square. If I have an area of 120 times 120, which is this, that means 14,400 is my perfect square. Okay, so the number actually goes on and on. All right, so if I go through this using counting numbers, all right, 1 is a perfect square, 4 is a perfect square, 9 is a perfect square, okay, right, 16 is a perfect square, 25 is a perfect square, 36 is a perfect square, 49 is a perfect square, because a perfect square can be square root. Okay, so the opposite of this is the length of a square, and we use a square root. Okay, so if we square root the 4, we get back our 2. If we square root our 100, we get back our 10. If we square root our 14,400, we get back our 120. Okay, so a perfect square is quite common in prime factorization. Okay, and it's a rather important concept in secondary school. Okay, so I'm going to go through this in my coming slide. Okay, express 3,675 as a product of its prime factors, giving your answer in index notation. This one no issue. Part B, hence states the smallest integer value of n such that 3,675n is a perfect square. Let's do A first, which is easy. All right. Okay, so 3,675 written as a product of its prime factors, right? This one we all know we have to use repeated division. So we have to recall what are all our prime numbers. So the smallest prime number is the 2, right? But unfortunately, 3,775 cannot be divided by 2. So we have to move on to a 3. Okay, so 3,675 can be divided by 3 to give us 1,225. Okay, now 1,225 cannot be divided by 3 anymore because it gives us a remainder. So we move on to the next higher prime number, which is a 5. So when it's divided by 5, it gives us 245. Okay, so this one, if I move on further, I get a 49, and 49 can only be divided by a 7. Okay, and we stop our repeated division when we arrive at a 1 here in the quotient. The final quotient is a 1, so we can stop. And the divisor on this side here becomes the factors of 3,675. So if I write this as a product, it looks like this. 3 appearing once, 5 appearing twice, 7 appearing twice. Okay, so it, remember, it's as a product. Product means multiply, right? So this one can be rewritten as 3, because 3 appear once means 3 has 1 power, and 5 appear twice means 5 to the power of 2, or 5 square, and 7 appear twice means 7 to the power of 2, or 7 square. So 3,675 is equal to 3 times 5 square times 7 square. So part A is completed. Easy, right? Okay, this is familiar to you. Okay, let's move on to part B now. Part B continues from part A So it has to use part A answer to do part B. All right. So they ask us to find out what is the value of n. N is the smallest integer, right? And it must be this n must be multiplied by 3675 to get a perfect square. We want this to be a perfect square. Okay, all right. So let me rewrite nicely. That means using index notation. Apology, I forgot the 7. Like that. So if I multiply it by n, I get a perfect square. Okay, so remember 3675 n is an algebraic expression and n is an unknown value. So when you multiply n to the product of the prime factors, we get a perfect square. Okay, so remember a perfect square is a number that can be square root. Okay, so let's take a look. 5 appear twice, so can be square root, because 25 appear twice means 25 can be square root. 7 appear twice means 49 can be square root. But unfortunately, 3 appear once only. So 3 cannot be square root. It gives us a decimal value. So how to make 3675n to be a perfect square? We need to multiply another 3 to this 3 to make it 3 to the power of 2. So this one has to be written as 3 times 3. This one, no change. This one, no change. Then the whole thing is now a perfect square. Okay, this is our original 3675. Okay, so what have we done? We have introduced another prime factor, which is a 3, and 3 must be the value of n. So part B is completed. So n is equals to 3. So when n equals to 3 is being multiplied to 3675, it make the new number 3675 and a perfect square. Okay, all right. I'm going to go through the next question number 2 to further help you to understand this idea of prime factorization involving square and square roots, perfect square and square roots. Okay, right. Let's take a look at question 2. Express 360 as a product of its prime factors, leaving your answer in index notation. Part B, find the smallest possible integer n such that 360n is a perfect square. And find the integer n such that 360n is a multiple of 16. Okay, let's do A first. A is easy. Okay, A should not be an issue. A is easy. Okay, so again, we should use our repeated division. Okay, do carefully, yeah. We must do this until we arrive at a 1. So this is 5. And finally, we end at a 1. Yes, we can stop. And the list of prime factors here should give us the product. So 360 is written as 2 appearing 3 times, 3 appearing 2 times only, and 5 appearing once. And it can be written in this manner for index notation, like that. Okay, let me take a look again. 2 appear 3 times, so it is a cube. 3 appear 1 time, so it is power of 1. And 5 appear, okay, let me redo this part. Okay, sorry, too fast. Okay, let me redo this. Okay, 3 appear 2 times, so to the power of 2, and 5 appear only 1 time. Okay, I think I'm correct now. Okay, so 360 is written as 2 cubed times 3 square times 5 alone. Okay, Right? So we have already completed part A. Okay, I'm going to move on to part B. B1. We are given 360n and we want it to become a perfect square. Okay, all right, so this is something that we are familiar with because it has been discussed in our previous slide. So I'm going to rewrite this using index notation from part A. So 360n is the same as 2 to the power of 3 times 3 to the power of 2 times 5 alone, and n means it's multiplied, and it's an algebraic expression, right? Okay, so I'm going to rewrite this even clearer for you to understand. It becomes 2 appear 3 times, okay? 3 appear 2 times, 5 appear once, and n appear once. Okay, now we want it to be a perfect square. Perfect square means we must have a pairing of factors. So let's pair them up. This is one pair. This 2 is alone. Okay, this 3, one pair. 5 is alone. Okay, so what is the value of n? N is very crucial in this case. We want n to be so special that the expression is a perfect square. So we want, in order for the expression to be a perfect square, this number 2 must have another number 2 so that it becomes a pair. So we need to introduce a 2. And we also want this 5 to be another, there must be another 5. We need to multiply another 5 to the expression so that it becomes 5 square. So n has the value of 10. Okay? Alright? So that means if we multiply 2 and 5, that means if we multiply 10 to the expression 360, we will get a perfect square. So n has the value of 2 times 5 equals to 10. So n is 10. Okay, let's take a look at part 2. Now, to do part 2, we have to borrow the 360n again. Okay, let me rewrite that expression. So 360n is this expression here, okay, the one that we did previously in our previous example. So 2 cubed times 3 square times 5 times n. Rewriting this clearly for us, I'm going to expand this so it becomes easier to visualize. Okay, we want to know what is this value of n such that it becomes a multiple of 16. We want it to be a multiple of 16. Now, what is the meaning of multiple of 16? That means the expression here can be divided by 16 perfectly. So to do this clearly properly, we have to know what are the factors of 16. So factors of 16 can be done using repeated division. This one I'm going to do very fast because it is easily done. Okay, we arrive at 1. Hey, too fast. We arrive at 1 here. So 2 appear 4 times. Okay, right? Okay, so 16 is actually appearing 4 times. So 16 is 2 to the power of 4. Like that. Now, in order for the number here, I'm going to put asterisk. In order for this number, this expression, 2 times 2 times 2 times 3 times 3 times 5 times n, to be a multiple of 16, the expression, the asterisk expression, must be able to be divided by 16. In order for it to be divided by 16, the two sets of factors must be quite similar. That means we should be able to see the factors of 16 inside the expression with the asterisks. Let's take a quick look, okay? Let's compare them. Okay, so 16 has how many tools? 4 tools. Let's take. Okay, this one will partner this. This one will partner this. This one will partner this. Okay, almost right. Uh-oh, no more tools already. No more tools because there's a short of a factor 2. That's why the asterisk 360 alone cannot be a multiple of 16. So in order for 360 to be a multiple of 16, we have to multiply by n, and n is the value 2. So when you multiply 2 to 360, when we do that, what are we doing? That means we get this 2 to the power of 4. Okay, let me rewrite nicely. This is our original expression in part A, right? Then when we multiply by 2, what are we doing? We are actually making this 2 to the power of 4. And 2 to the power of 4 is this. It's already 16. That means there is a 16 in this new equation. Okay, so we can conclude that n must be 2. When n is equals to 2, that means 2 is multiplied to 360. We already have 16 in the prime factors, the product of prime factors. Okay, so comparison. Okay, so we don't have to worry about what's here. No need to worry. Our job is to make sure that, all right, okay, one more time. Our job is to make sure that this part is okay. So we just need to introduce this to the 360. So when you introduce 2 to the 360, when we take 2 multiply to 360, we already get the new number 360n to become a multiple of 16. Okay, all right. So remember, play back my video to get a better understanding. Okay. All right. So in my video, I've shared with you 2 examples, right? 2 questions involving prime factorization and to solve questions involving square roots and perfect squares. Okay, I hope you can find it useful. Now, in my coming videos, I'm going to share with you perfect cube and cube root. Now, everyone, remember to subscribe to my channel, because when you subscribe to my channel, right, you'll be notified of all my new videos being uploaded. Okay, if you like my today's sharing, give it a thumbs up, a like. I strongly encourage you to give me your feedback, your motivation, right? So your motivation helps me to move on, to keep on improving my videos, to share with you more videos, so that it assist you, help you in your secondary school work. Okay, and your valuable feedback help me to improve, help my work, help my future videos to be better. And kindly don't be shy, share with your friends. Okay, right, thank you for watching my video, thank you for following me, thank you for subscribing. Right, till then, this is Joseph. Goodbye.